Hello, I really need a better setup for this, but today I wanted to explain a little bit about science color theory and not really explain it, but just try to delve into it and understand it better myself. Dad asked me a question of, "Hey Katya, well, if I want a hot pink circle on the computer screen," he says, "what combination of red, green, blue pixels do I need?" And in the older screens, which are simpler to explain, each pixel could either be red, green, or blue, and the percentage of red, green, and blue pixels would creates different colors. And it's simple for a color like red or green. It's just 1, 0, 0 or 0, 1, 0 if you want green. But what if you want a stranger color like indigo or violet, Miami orange? That's a great question, and I said to him, "You should just Google it." I realized that's a pretty bad answer. So I googled it. It all started with Maxwell, and Maxwell built on the theories of color from Newton and Young. Maxwell did is he took 3 pieces of paper, and he took these 3 pieces of paper and stuck them on a wooden disc, which is like this, and just cut them into pieces to create some sort of combination. And then spin them around and see the color that they would produce. So if it was 1/3, 1/3, 1/3, then theoretically he saw white. Maybe figure out what the fractions of colors were for the 7 main colors of the rainbow. But what if you had a color spectrum with hundreds of colors? In 1913, there was an organization called Commission Internationale de l'Éclairage, and they are the international authority on color, so who knew that exists? So what they did in 1931, do all these factors relate into our perception of color? So you have the wavelength of light, type of light, like spectrum of light, spectral radiance. That's essentially the power deposited per unit area per wavelength. Okay, so I'll call this like SR, eye, and the brain, because that's what makes color science so complicating. And then how do we put these together into what we actually see as a color? The CIA took in the data of spectrum, wavelength, and eye information and made this nice graph, and you can choose any wavelength on the graph and find the corresponding little x, little y, which are ultimately your R and G coordinates, and you can find your B coordinate because all 3 are supposed to sum up to 1. But then the question is, well, how did they make this really nice graph? And that's where all the functions come in, the actual transfer function, you can call it, from your wavelength data to your RGB data. Functions itself are not too bad. Okay, so, and this is over your wavelength. So let's say I choose a wavelength. I want a wavelength of 475, which is blue. Okay, and you have to choose a range, so it's not really discrete for whatever reason. So you do like 470 to 480 when you integrate. So this actually is your color data for the eye. You see those functions on the left, and on the right, those are the functions x bar, y bar, z bar, which describe the sensitivity of the eyes, so the actual cones. And actually, interestingly enough, you can see that the blue cone can actually pick up some red and green as well, which is why it's, again, a nonlinear system. By the way, a paper that I saw online by Chris Wyman actually has the analytical equation for those color eye functions. And then the last variable, which is the capital L, that's the spectrum data, so it's called the radiance curve. And on the right side, you see there's a black body radiance spectrum, so that's pretty much what you would plug in if it's a black body, and it depends on the type, so a lamp or maybe a star. And just to remind you, we started with wavelength, and now we have this big x, y, and z from the integration. And now, in order to find the little x and the little y that we saw in the graph, you actually just kind of normalize that data, which is pretty simple. So you take the big X that we saw divided by the total, and there you go. Somehow now you have a linear map that a computer display system can use. And actually, interestingly enough, this XYZ, that is the CIE standard, but now the TVs and computers have kind of their own different systems. Each system, NTSC or EBU, have their own XR, XG, XB, the little matrix on the left, and you have your XYZ, those are the CIE coordinates, so the matrix on the most right in equation 3, and then they just have to figure out the weights, which is a simple matrix operation, and there you go. That's how you take the crazy complicated information of the eye and turn it into a linear system that can be replicated on any screen. Thanks for watching, and there's more info in the links below.